Reductio ad absurdum, you nerdums. Let's talk about the intermediate value theorem. A preliminary result to get us started. Suppose that f of x, a continuous function on an open interval, and x naught is a point in that interval, so that f of x naught is less than L. For some L, it doesn't really matter what L is, but it's bigger than f of x naught. Then there must be an open interval containing x naught on which f of x is less than L. So if f of x naught is less than L at a point, then there's an open interval around that point on which f of x remains less than L. Now, as a picture to sort of back this notion up, I'm going to draw my generic picture of a continuous function. Now observe, if I put, for example, L is this height right here. Let's find a point where f of x is less than L, maybe this right there. So here is our x naught, and indeed, you can observe f of x naught is smaller than L. The theorem says what's guaranteed to happen is I'm going to be able to find an open interval around x naught, and on this entire interval, f of x remains less than L. So the fact that the continuous function was smaller than L at one point means it's going to be smaller than L at a little interval around that point. So suppose to the contrary that there isn't such an open interval. In other words, for every open interval from x naught minus epsilon to x naught plus epsilon, there is a point where f of x is bigger than or equal to L. So no matter what epsilon you pick, I can find a point x within epsilon of x naught so that f of x is bigger than or equal to L. If I can do it for every epsilon, I can do it for 1 over n, a half, a third, a quarter, and so forth. So for each epsilon equals 1 over n, I find a point xn within distance 1 over n to x naught. There's our first inequality. But all of these points satisfy f of xn is bigger than or equal to L. But observe from the squeeze law, the xn's are distance 1 over n to the fixed point x naught, which means that as n goes to infinity, xn has to converge to x naught. However, the sequence f of xn, first of all, it might not have a limit, but if it does, since all the f of xn's are at least as big as L, the limit must be at least as big as L as well. That contradicts the fact that the function is continuous at x naught, because we have a sequence xn converging in the domain to x naught, but in the range, f of xn can't be converging to something less than L if it's not converging, or if it's converging, it has to be converging to something bigger than or equal to L. So yes, a continuous function, if it's smaller than L at a certain point, can't jump to be larger than L at arbitrarily close points. The strict inequality is absolutely necessary. For example, I can draw a nice continuous function. Here's f of x. Okay. Here is going to be my height L, and here is x naught. It's true that f of x naught is less than or equal to L. It happens to be equal. But now if I take any open interval around x naught, I'm definitely going to include values bigger than L. So it was very important in our proof that at our point x naught, we didn't have f of x naught less than or equal to L, but strictly less than. Here are a couple variations on this theorem. If we are continuous on an open interval and less than L, and f of x naught is less than L, then there's an open interval on which f of x remains less than L. That's the one we already did. But you can replace those less thans with bigger than. You can also invoke left or right continuity at certain endpoints. So here is one, for example, using right continuous at the point x naught. And here are two versions using left continuous at the endpoint x naught. And here is the statement of the intermediate value theorem. Suppose f of x is continuous on the interval from a to b, including its endpoints. Notice that this is a bounded closed interval, aka compact. x naught and x1 are 2 points in this compact domain, so that f of x naught is less than or equal to f of x1. If I pick 2 points in the domain and evaluate the function, one of them is going to be bigger than or equal to the other. I'm just declaring f of x naught less than or equal to f of x1. Then if you pick any y value in between those two, there must be some x prime in between the two x's, so that f of x prime equals y. And if x0 happened to be less than or equal to x1, we're going to use the interval from x0 to x1. If x1 happened to be less than or equal to x0, we'll use the interval from x1 to x0. Notice I assumed f of x0 is less than or equal to f of x1, but in doing so I lost the ability to assume whether x0 itself was less than or equal to x1. You can make the assumption without loss of generality on one of those inequalities, but not the other. I just elected to assume f of x0 is less than or equal to f of x1, but now I have two possibilities for how does x0 compare to x1. Here's the basic idea. So suppose you have got a compact domain, which for us just means closed bounded, and we're just going to go ahead and assume a closed bounded interval. So here's my domain. I've got a function, and it's continuous. Now what I do is I pick, I don't know, here's x0 and here's x1. Okay. So observe that f of x0 is this height, f of x1 is this one, which is bigger. So I do indeed have f of x0 is less than or equal to f of x1. So pick something in between the two values, and this is a y value, so I'm going to pick, say, this one right here. Here's my y. It is in between f of x0 and f of x1. Then there must be some point x prime in between x0 and x1 where f of x prime is exactly y. That's what we're going to prove will always happen. Let's assume for the sake of argument that x0 is actually less than x1. If it's the other way, just reverse everything in the proof that comes. And pick a y in that range. Define the set A to be all points down in between the 2 points you picked, in between x0 and x1, where f of x is less than or equal to y. Remember, our goal is to show that I can find a point where f of x equals y. I'm going to look at the set of all points where f of x is less than or equal to y. It's definitely not an empty set. Okay, our assumption was that y was picked to be in between f of x0 and f of x1. So f of x0 is definitely less than or equal to y. So x0 is definitely in A. Now it's a subset of the interval from x0 to x1, because it was only points in the interval from x0 to x1 where something happened. So it's a bounded set. Okay. I now have a bounded non-empty set of real numbers, so it has a supremum. I'm going to call the supremum of A alpha. A is the set of points in between x0 and x1, where f of x is less than or equal to y. Alpha is the supremum of that set down in the domain. What we're going to prove is that f of alpha equals y. Now here's what we have so far, just to refresh. x0 is less than or equal to x1. I picked 2 points down in the domain. F of x0 is less than or equal to f of x1. I assumed that was the relation between the f's, and I'm just assuming for the sake of argument x0 is also less than or equal to x1. Y is chosen to be in between f of x0 and f of x1 up in the range. I define the set A to be those points down in the domain where f of x is less than or equal to y, and alpha is the supremum of that set. So, drawing a pretty similar picture as we had before, here's our function. Okay, here is my x0, here's x1. x0 is less than or equal to x1 now. F of x0 is less than or equal to f of x1. I pick some y in between. And then I ask, what are the points down in the domain that evaluate to be less than or equal to this? It's a set, and I'm saying that the supremum of this set here actually evaluates to y. Let's assume it doesn't. Okay, if f of alpha isn't y, then it's either less than it or bigger than it. If f of alpha is less than y, what we've shown is there must be an open interval around alpha where f of x remains less than y, meaning I can move to the right and still be less than y. So alpha was not the supremum of the set of points that don't exceed y. If f of alpha is less than y, then I can move slightly to the right and remain less than y, so alpha is not the supremum of points that evaluate to be less than or equal to y. But conversely, if f of x is bigger than y, the same argument says I can move slightly to the left and remain bigger than y, meaning that this also isn't the supremum of points that evaluates to be less than or equal to y, because there's a whole interval to the left that is also too big. So if f of alpha is too small, I can move to the right and still be too small. If f of alpha is too big, I can move to the left and still be too big. So either way, f of alpha can't be less than y, it can't be bigger than y, so it had better be equal to y. Okay. This was if alpha is not one of the endpoints, because I needed to move left and right. But we've established in earlier slides that this inequality result about continuous functions can be applied at endpoints in the appropriate way. So if alpha, the supremum of the set of points where f of x is less than or equal to y, happens to be one of the endpoints, the same argument works with minor modifications. So yeah, if a continuous function takes two values, it has to take every particular value you can find in between. It can't somehow skip a value. This does rely on the domain being compact, but also having another property. Yeah, it does make sense. You don't want a continuous function to just miss stuff. And yes, in addition to making sense, it happens to be a true result. Now, I said that the domain has to be compact and also something else. So let's take a look at the following function. The function is 0 from 0 to 1, and the function is 1 from 2 to 3. This is a continuous function on a compact set. The set is closed and bounded, and therefore compact. The function is continuous at all points, including left and right continuity at various endpoints. But it doesn't satisfy the intermediate value property. Here's a picture of what this function looks like. It is this value here, then it is this value there. So why is this function continuous everywhere? Well, down in this interval in the domain, if I take any points, I'm getting a nice constant value. And if I take any points here in the domain, I'm just getting a different constant, but there's no sudden jump like we saw in functions that had a behavior like this, where approaching from one side and approaching from the other gave two different limits. Because these two intervals are separated from one another, this endpoint here can only be approached from one direction, and this endpoint here can only be approached from one direction, but they're not the same point, so you're not going to get a contradiction-generating jump in values. But there's no value taken by the function in between 0 and 1. It had value 0 and then it had value 1, and it's continuous, but it doesn't take any value in between. So the intermediate value property is not satisfied. The domain was compact. It was closed and bounded, but there was a gap in the domain. It's not what is called a connected domain. Now, the distinction of what sets are connected and what aren't, honestly, is not something that we want to get into here. For our purposes, we're just going to use the intermediate value theorem in the sense of the function was continuous on the closed bounded interval from a to b, which is compact and connected. We're not really going to do a full exploration of the topological version. I mean, it might seem clear what it means for a set to be connected, but it's still a technical definition and we don't want to get into it. It's just not a focus for us. It's a little beyond what we want to get into. One consequence of the intermediate value theorem is as follows. Every polynomial of odd degree has a real root. If f is a polynomial of odd degree, let's say the coefficient is a, which can't be 0. The leading coefficient can't be 0, otherwise we would have called it a smaller degree. So what one can show is that as x goes to infinity, x goes to the sine of a times infinity. Remember, the sine of a is 1 for a positive number or -1 for a negative number. So if the leading coefficient is positive, as x goes to infinity, f of x goes to plus infinity. If the leading coefficient is negative, it goes to minus infinity. And for x going to minus infinity, it reverses. There's an extra minus sign out in front. It's very crucial that the polynomial be of odd degree here. So this is a little exercise to prove these things. The gist is as follows. I've got a polynomial of odd degree, and I'm going to draw my traditional cubic. Well, here's a cubic whose leading coefficient is positive. As x goes to infinity, the function goes up to infinity. As x goes to minus infinity, the function goes down to minus infinity. Now, I don't know exactly where the x-axis is, the line y equals 0, but it's got to be somewhere. Meaning, if I go far enough to the right, I'm eventually positive. If I go far enough to the left, I'm eventually negative. And now I have a continuous function. Remember, polynomials we've seen are continuous everywhere. So it's a continuous function on this closed bounded interval, just go slightly to the left and slightly to the right. it was negative, then it was positive, so it must achieve every value in between, including 0. That's really the proof. So yeah, since the limit as I go to the right is infinity or minus infinity, and the limit as I go to the left is the opposite, I can find a really big number so that f of n and f of minus n are opposite sign of one another. One of them is positive and one of them is negative. And therefore I have the closed, compact, connected interval from minus n to n on which polynomials are continuous because they're continuous everywhere. Negative at one endpoint, positive on the other, therefore it must be 0 somewhere in between. So every polynomial of odd degree has at least one real root. Another nice theorem we get out is something called the Brouwer fixed point theorem. Suppose A is a compact interval and f is a continuous function whose codomain is also A. So for every point in A, f of x is also in A. Then f has what's called a fixed point, a solution to f of x equals x. So it wasn't just a compact set, note in the statement of the theorem, it's actually a compact interval. So it's some closed bounded interval, let's call it from A to B. Since the function goes from A to B into A to B, f of A has to be at least as large as A, and f of B can't be any bigger than B because the range has to be a subset of A to B. So we've got down in the domain some sort of A to B, and up in the range I have the same set from A to B. I'm just drawing them on different axes. Now what does f of x do? I'm not exactly sure, but it's got to be continuous. So f of A has to be somewhere in this range of heights. F of B has to be somewhere in this range of heights. The function is continuous. Whoops, I made it go too large. Okay, it can't go beyond B, so just imagine that this is less than that. And what we're saying is, somewhere in here there's a solution to f of x equals x. Now remember, we tend to draw f of x as on the y-axis. So we're trying to solve where is y equal to x. Well, that's just going to be the line y equals x, and it's going to have an intersection. That's basically the proof, and let's see how it works. We're going to define g of x to be the function f of x minus x. Since f of x was assumed to be continuous, and x is a polynomial of degree 1, which is continuous, the difference is continuous on the same interval. Now f of a was bigger than or equal to a, so g of a, which is f of x minus x, is f of a minus a, is positive, or at least not negative. Similarly, since f of b was less than or equal to b, g of b is less than or equal to 0. So g is continuous from a to b. It's bigger than or equal to 0 at the left endpoint, but less than or equal to 0 at the right endpoint. By the intermediate value theorem, there must be a point in between where it's equal to 0. But what does it mean for g of x to equal 0? Since g of x is f of x minus x, if g of x equals 0, it means f of x equals x. So there is some point where f of c equals c, aka a fixed point. Now, if you've heard the phrase the Brouwer fixed point theorem, it is actually much more than this. This is the very special case of the Brouwer fixed point theorem in the real numbers with one dimension. And the proof is fairly straightforward. The proof in higher dimensions or in other spaces can be a bit more involved. But for our purposes, hey, we're only doing single variable calculus in the real numbers. So for us, this is good enough. And since it happens to be the Brouwer fixed point theorem in R, that's what I've called it, the Brouwer fixed point theorem. Let's talk about inverse functions. Okay, suppose I have a non-empty open interval. A lot of stuff is true about the empty set for silly reasons, so we're not dealing with an empty interval, but it is open. And f is continuous and invertible on A. If I have a invertible continuous function on an open interval, we are either strictly increasing or strictly decreasing. So to show a function is strictly monotone one way or the other, what we're going to do is we're going to assume A and B are 2 points down in the domain which aren't equal. Since they're 2 different points in the domain, I'm just going to say that A is less than B. Now f is invertible, which means f of A can't equal f of B. For the sake of argument, assume that f of A is less than f of B. It can't be equal because it's invertible, so I never get the same thing out twice. So therefore f of A is either bigger than or less than B. Let's just assume it's less than. So A is less than B, f of A is also less than f of B. Now what we're going to show is that the function is strictly increasing on A. If, however, f of A was larger than f of B, we'd have a decreasing function. The proof would proceed more or less the same. Okay, so what we have is, we have an open interval, which is our domain, non-empty. I pick 2 points in here. Let's call them A and B, and I've assumed that f of A is less than f of B. Now here's the basic gist. Okay. I claim the function is strictly increasing. It's going to proceed in several steps. First, it's going to be strictly increasing from A to B. So pick 2 points in between A and B, possibly equal to the endpoints. If the left endpoint happened to evaluate to be higher than the right endpoint, in other words, it doesn't remain strictly increasing. I can plug in a lower number and a higher number, but have that be reversed when I apply the function. The intermediate value theorem is going to say, I take all these values in between, then I take all these values in between, and this will violate that the function is invertible because I would have had to have achieved the same value twice. If we can show all that, what we'll get is that the function is strictly increasing from A to B. But we claimed something more, that it's strictly increasing on the entire domain. So you have to do a kind of similar argument saying, okay, now pick some point here, let's call it C. If f of c was smaller than f of b, well then you could generate a very similar contradiction by saying, pick some value like this, and note that I'm again going to violate invertibility. Therefore, f of c has to be bigger than f of b. That's going to get us that I'm increasing all the way to c, and a similar argument gets me increasing all the way to the left. Patch that all together, and you're increasing on the entire domain. But it's going to take a bit. So prepare yourselves, this is going to take a bit. Pick any c which is in between the 2 points a and b. We claim that f of c is also in between f of a and f of b. Now we have assumed that f of a is less than f of b, the outer inequality holds. And since the function's invertible, we never get equality out. So if our desired chain of inequality fails, if f of c isn't in between f of a and f of b, either it's smaller than f of a or it's bigger than f of b. Let's just assume that f of c is smaller than f of a, and we already know f of a is smaller than f of b. If, on the other hand, f of c was larger than f of b, the proof would proceed very similarly. So the function can't jump up and then come down, because that would violate invertibility. Yeah, it is tricky to put this together in a proof kind of way, but the intuition is there. To summarize, a is less than c is less than b. C is in between a and b, but f of c was outside the interval from f of a to f of b, and we've assumed it was off to the left. Pick a value of y that's in between f of c and f of a. Since f of c is smaller than f of a, I can find a real number in between the two. Then there must be some value of x so that f of x1 equals y in between a and c. That's the intermediate value theorem. But since y is also in between f of c and b, there is some point in between c and b so that f of x2 equals y. This is exactly the picture that was drawn earlier, just phrased more formally. In other words, we had a, b, c, f of a, f of b, but we assumed f of c was in fact smaller than f of a. So pick a value of y in between these two, and notice that it's therefore also in between those two. So by the intermediate value theorem, we're going to find some point here and some point here that evaluate to the same height, and therefore contradict invertibility. It's also worth pointing out that the places where f of x equals y had to be in between a and c and in between c and b, but couldn't have actually been c, because remember, y was chosen to be in between f of c and f of b, or f of c and f of a. So therefore, f of x1 being equal to y means x1 is not equal to c, and x2 is also not equal to c. So therefore, I have two different points. x1 is strictly less than c, and x2 is strictly bigger than c, that both evaluate the same y, which violates invertibility. What we have so far, if f is continuous and invertible on an open interval, and I have a is less than b and f of a is less than f of b, then any f of c must be in between. No, we are not done. We're actually not even especially close. It does seem like a fairly straightforward result, okay? To be invertible, you've got to be strictly increasing if you're continuous, or decreasing. Now we claim f is in fact strictly increasing all the way from a to b. If I pick any 2 points in between a and b, let's just say a is less than c, c is less than d, and d is less than b, we know f of c and f of d are both in between f of a and f of b. That's the proof we just did. Pick a point in between a and b, f of that point will be in between. Okay, so we have both f of d and f of c in between f of a and f of b, but furthermore, since c is in between a and d, and f of a is less than f of d, then f of c is in between f of a and f of d. Again, that's just what we just proved. So what we've got so far is as follows, okay? On the previous slide, we said, suppose I have a is less than b, f of a is less than f of b, and I've got a continuous invertible function. Pick any point in between, it will evaluate to something in between. Now what we have extended it to on this slide, if I pick 2 points c and d in between, f of d has to be somewhere in between f of a and f of b by applying this reasoning. But now forget everything in between d and b. And just look, I've got f of a is less than f of d, continuous, invertible, therefore f of c is in between f of a and f of d. So if you pick any 2 points in between, f of c will be less than f of d. That says the function is strictly increasing from a to b. Any 2 points you pick in between, f of the left will be smaller than f of the right. That gets us to right here. Okay. But now what we want to do, having established that the function is increasing from a to b, is to keep moving off to the right. So pick a c which is larger than b, something off beyond that. We want to show the function is still increasing. In other words, f of c is bigger than f of b. Well, if it isn't, okay, if f of c is not bigger than f of b, it certainly can't be equal to it because we're invertible. So f of c is smaller. Either f of c is smaller than f of b, but not smaller than f of a, or f of c is actually smaller than f of a. Again, it can't be equal to it because we have an invertible function. But in either case, I can find a y value that's going to generate a contradiction in between the 2 larger values, depending on which chain of inequalities we get. Either pick something in between f of c and f of b, or in between f of a and f of b. Based on the intermediate value theorem, we're going to find 2 points where we get the same height. It's really the same argument as before. Okay, so if I had a, b, and now off to the right is c, f of a is less than f of b, and f of c is like way down here. Okay, if I pick a y value, it's got to cross it once here and then cross it again there, and I'm going to violate invertibility. Which just means any 2 points I pick, a and b, if a is less than b and f of a is less than f of b, not only is f increasing on the interval from a to b, but any point to the right also generates something bigger than f of b. But now I can apply the same reasoning we already had. What we've shown is that if the function is continuous and invertible from a to b, f of a is less than f of b, then the function must be increasing on this interval. We've also shown if I pick something larger than b, it's bigger, f of c will be larger than f of b. But now I apply that same reasoning over here. I've got a continuous increasing function from b to c. F of b is less than f of c, therefore I'm increasing all the way in between. So if I move to the right at all, I am increasing all the way from a to b and then from b to c as well. So we're increasing from a to c. Okay. And we're almost done. If you do something very similar, and the word similarly, by the way, is math speak for, gosh, we could show it, but it's so repetitive and we've already done so much. So moving to the right of b kept increasing. Moving to the left of a is going to be decreasing. It's almost an identical argument. So now what we have is, here is this big open interval on which we are invertible and continuous. We picked an a and a b, and we assumed that we had f of a is less than f of b. First we showed you must be increasing here. Then we showed if you pick any point c, you're also increasing here. If you pick any point d, you're also increasing here. The minor distinction that we have to be careful about is our domain was open on both endpoints. So I can't actually talk about f of the endpoints of my domain because they might not exist. But if I keep pushing this left endpoint down and pushing this right endpoint up, we'll reclaim the whole thing. So that's what we're doing now. We're making 2 sequences. Alpha n starts at a, okay? As alpha naught starts at A, beta naught starts at B, alpha n then decreases down towards this left endpoint, and beta n increases with limit this endpoint. But every time I pick a particular endpoint, I'm increasing on the whole interval in between them. Okay, so I'm just going to redraw that picture over here so it looks a little nicer. Our domain, big open interval. We picked an A smaller than B, assumed f of A was smaller than f of B. The big first step was to conclude that we're increasing all the way from A to B. Then what we did is we showed if you take any cutoff point to the right of B, you're still increasing there. If you take any cutoff point to the left of A, you're still increasing there. So we're going to call these alpha n's and we're going to call these beta n's. These are going to increase up to this right endpoint, and these are going to decrease down to this left endpoint. Anytime I make a particular choice, I am increasing on the whole interval. And the endpoints have limits, which are these endpoints of the domain. So since f is increasing on each of those intervals, if I take any 2 points in between alpha n and beta n, I'll have the correct inequality. But since alpha n converges to the infimum of A and beta n converges to the supremum of A, any 2 points in A will eventually be in between these two things. Alpha n is going to, x1 is going to be bigger than alpha n, not less than, sorry. So since any 2 points I pick, x1 and x2, are eventually in between one of these alpha and betas, and the function is increasing on all intervals from alpha to beta, eventually I'm going to be able to trap any 2 points I want in one of these intervals and therefore satisfy the correct inequality. Therefore, the function is strictly increasing on the entire domain. And we're finally done. The real difficulty here was just that our interval, our domain, did not necessarily contain its endpoints. There was a lot of work to get around that. Continuing with inverses, suppose A and B are open intervals so that f maps A to B is continuous and invertible. Then the inverse is also continuous. It's an invertible function. We're just saying if a continuous function has an inverse, its inverse is also continuous. Now what we do know is that the domain A was an open interval and f is continuous and invertible, therefore it is either strictly increasing or strictly decreasing. Let's assume f is strictly increasing on its domain. Now what we get, the function is strictly increasing. So if I plug in a smaller versus larger, x1 is less than x2, I get out a smaller versus larger, f of x1 is less than f of x2. The function's invertible though, so if I just be a little creative with my notation and let y1 be f of x1, y2 be f of x2, and just go backwards, okay? Notice then that y1, if that is bigger than or equal to y2, then the inverses must satisfy the same thing. Okay, instead of going from left to right in these two inequalities, I'm going from right to left, but because I'm invertible, that's really not a big deal. So therefore, it must be strictly increasing. The inverse, that is. Okay, and here's a picture to sort of, follow up on what we just said. So our function is continuous and increasing. Now, if I try to graph the inverse of this, so notice what I mean is if I plug in a small input versus a big input, I definitely get out a small output versus a big output. However, the inverse function just reverses the idea of what's in versus out. It just reverses domain and range. But it's going to satisfy the same thing. The bigger number here corresponds to the bigger number here. Whether I'm going from the domain to the range or from the range to the domain via the inverse function, I'm going to be preserving the same increasing property. So take an arbitrary point in the codomain in B. Suppose I have a monotone sequence converging to it in the range B. The corresponding sequence, being xn's being the inverse of them, must also be monotone in A. Now, if f and f inverse are strictly increasing, and the y-n's were increasing to their limit, then the sequence xn is increasing, okay, but also bounded above by the ultimate limit f inverse of y. So therefore the sequence converges to something. We just want to show it converges to the correct something. In other words, the inverse function is definitely monotone increasing. We just want to show it's also continuous. That's the real work here. Increasing functions have increasing inverses. That's quite straightforward. The picture I drew basically is the proof. We just need to prove it's also continuous. Now f is a continuous function. Therefore, if I have a sequence in A which converges, specifically the xn's in A are converging to some x prime, since f is continuous, the limit of f of xn must be f of x prime. But f of xn was just yn. That was just a notational thing. Theyn's I simply declared to be f of xn's. And the limit of yn was assumed to be y. So f of x prime must equal y, but the function's invertible, so x prime must be f inverse of y. So anytime a monotone sequence in B converges to y, the sequence f inverse of yn converges to f inverse of y. Let's see a picture. Okay, so I'm going to draw pretty much the same invertible function we had on the previous slide. Okay, so here's my invertible increasing function, continuous as well. But notice, here is my set A, and here is my set B. I'm interested not in the fact that the original function is continuous, but in its inverse function. And I'm going to do it using the sequence-based version. I'm going to take a point here in B, and I'm going to take a monotone sequence converging to it. Let's say yn is converging to y, and it's increasing. Each yn gives me an xn here. Okay, but since the original function is increasing, so is its inverse. So if theyn's are increasing, then the f inverse ofyn's are also increasing. I'm going to call these xn's. Now I have in the bounded set A an increasing sequence xn, so the xn's have a limit. What's the limit? I don't know. Let's call it x prime. What we're trying to show now is that y plugged into the inverse function must be x prime. If this sequence was converging in the domain of the inverse function, then this sequence is converging to the correct thing in the range of the inverse function, aka the domain of the original. Okay. And what we argued was the xn's are converging to something, so call that something x prime. But f, the original function, was continuous. So since xn converges to x prime, therefore f of xn converges to f of x prime. F of xn was just yn, and we already know yn is converging to y. Therefore f of x prime must equal y, and if I apply the inverse function, I get exactly what we wanted up here at the top. F inverse of y is x prime. So not only is the inverse function increasing, the inverse function is continuous as long as I'm only talking about monotone sequences converging to y. But we showed a while back a sequence converges if and only if all monotone subsequences converge to the same limit. And we've shown that we have the desired limit properties for all monotone sequences. So through that older result, we get that we actually have the correct limiting behavior for all sequences. Take any sequence you want converging to y. Every monotone subsequence is going to do the correct thing. Therefore, every monotone subsequence of the sequence of x's you get out will have the correct limit. Okay, it's a couple more lines of work, but you do get this out. Any sequence ofyn's converging to y, the corresponding xn's will converge to f inverse of y. Therefore, f inverse is also continuous as well as increasing. That really was the point of the previous result. I mean, that previous mess where we showed that if a continuous function is invertible, then it's either strictly increasing or decreasing. Really, the point was to get to this, that if a function is continuous and invertible, the inverse function is also continuous. The fact that they are also strictly increasing or decreasing was handy along the way, but what we're actually going to rely on as time goes forward is inverses of continuous functions are automatically continuous. So at long last, we finish up this discussion of the intermediate value theorem, but come on back, we're going to keep talking about math. Why would we talk about anything else? you.